Hello and welcome to your second year in secondary school. I am Ahmed Amin and it's a pleasure to be your lecturer for this physics course. Your syllabus for this year is very simple, but the last unit in senior 1 was talking about work and energy, which is a very important concept to be fully understand and it's important to be discussed. So this year we will start talking about work and energy. But first we need to refresh some important physics concept that you have studied before. From your previous study, you know that physical quantities can be classified into scalar physical quantities or vector physical quantities. Scalar, it's a physical quantity that can be fully defined by its magnitude only. It has no direction. But here we have magnitude only and no direction. For example, mass, temperature, time, length. All these physical quantities can be fully understood and defined by its magnitude only. If we are talking about temperature, its magnitude say 27 Celsius, it's enough to describe the temperature fully because we mention its magnitude and its measuring unit, just like that. The other physical quantities or the other classification or the other type was vector physical quantities. It's a physical quantity that can be fully defined by its magnitude and direction. Here we have magnitude and direction. For example, for vectors, force, displacement, velocity. If you are talking about velocity, its magnitude, say 50 km per hour, isn't enough to describe the velocity fully because we mentioned its magnitude and its measuring unit, but we didn't mention its direction. The other important concept we need to know is vector analysis or resolving the vectors. If we have an object here and it is affected by force in this direction, inclined force by angle theta, this force can be resolved into two components, Fx and Fy. In x direction, which is horizontal component, and it is F cosine theta, and here Fy, which is equal to F sine theta. Remember, if you have right angle triangle and this angle is theta, this is the opposite and this is the adjacent, and this is your hypotenuse. If you need to have sine theta, it will be opposite over hypotenuse, and you have cosine theta, which is equal to adjacent over hypotenuse. So remember, if you have to find the vertical component, it is the opposite to the angle, so we take sine theta. If you need to have or you need to find the horizontal component, we will take cosine as it is the adjacent to the angle. If we reverse the angle and say that theta is here, this force is gonna be F cosine theta and this component gonna be F sine theta. The other important concept is product of vectors. We have dot product and cross product. If you have two vectors just like that, here is vector B and here is vector A, and the angle between them is cosine is theta, and we have the dot product written like that, A dot B, and it's gonna be A P cosine theta. The dot product, remember, it produces scalar quantity. While cross product can be written like that, A cross B, it's gonna be A B sine theta n, and n is a unit vector, so cross product produced vector quantity. So we have scalar quantities produced from dot product and vector quantity produced from cross product, and remember that n is unit vector, which is normal to the direction of A and the direction of B. So let's dive into our new topic. From the first glance at the word work, it seems that it's an activity in which one exerts strength or faculties to do or perform something. But the term work in physics is different from that used in our daily life. Work doesn't mean that a tough task is done. To do work on a body, the body must move in a certain displacement due to the force acting on it. Let's see that. The meaning of work in physics different from that used in our daily life. Work does not mean that a tough task is done. The body must move in certain displacement due to the force. So if you need to have work, you need two conditions to be done: an acting force on the object and making sure that this object is moved a displacement. So we need acting force and a displacement in the direction of the force. That can be illustrated by the following two examples. The player who lifts weights up does work. Why? The force acting on the weight moves them upward through a distance in the direction of the force. He lifts the weight, was here, and he lifts it up. So we have force in his arms and displacement to reach that height. If a person like this kid pushes the wall, he does no work. You see him doing you see him doing activity. You see him exert strength. You see him facing faculties to push the wall, and he's tired. But that doesn't mean he do work, as work in our daily life is different from work in physics. Okay? Is there any problem? There is no work here, but we have work here. So the conclusion for that: when a force acts on an object to move it through a certain displacement in the direction of force, it is said that the force does work. If the object doesn't move, there is no work. If we have no force, there is no work. Work need the two things: force and displacement. So we need to have a definition for work in physics. Work is said to be the dot product of the acting force and the displacement d in the direction of force. If you have an object here and force in this direction, and the object is moved till it reaches this position, here is the displacement, and the force is inclined by angle theta. Here this component is F cosine theta, and this component is F sine theta. We're interested in the horizontal force, the horizontal component, and because it is in the direction of displacement. So work is F dot D, which can be F D cosine theta. What is the unit of measuring work? Work is measured in joule, and it will be equivalent to Newton dot meter, Newton for force, meter for displacement, joule equal Newton meter, and it's dimensional, or it can be equivalent to kilogram meter squared per second square. And remember that F equal MA, so Newton is equivalent to kilogram meter second power negative 2, and if you substitute by Newton here, you have this kilogram meter second power negative 2. Its dimensional formula is ml squared t power negative 2. This is the dimensional formula for work. So the definition of work is it is the dot product of the acting force and the displacement in the direction of force. From here we can find that work is a scalar physical quantity, as it is the resultant is dot product of force and displacement, and you know that dot product, I have remembered you, dot product produce scalar physical quantity. So work is scalar quantity. As work is a scalar, it can be positive or negative or zero. The point after that is what are the factors affecting the work. Number one is directly proportional to the force acting on it. Work is directly proportional to the force acting on it. If you want to represent that graphically, we have here work and we have here force. It's gonna be a straight line like that from the origin. As the force increases, the work increases. Number two, work is directly proportional to the displacement of the body. Work is directly proportional to the displacement at constant force, an angle between the force and displacement. If you want to represent that, we have here work and here is the displacement. It's gonna be a straight line just like that. The third point is cosine, the angle between force and displacement. If you want to represent that graphically, it's gonna be work and cosine theta. It's gonna be like that. And remember, the maximum value for cosine is 1. Cosine theta is less than 1 and greater than or equal negative 1. We can't exceed 1 for cosine theta. It's a mathematical error. We said here work can be positive, negative, or zero. How that could be possible? It's due to the effect of the angle between force and displacement. If the force is here and the displacement in this direction, you have object and you pushes this object with horizontal force. Here work will be F D cosine theta, and the force is parallel to the displacement, so theta gonna be 0. So work is gonna be Fd, and it is the maximum work. Work done is maximum when the direction of force is the same as the direction of the displacement. The second point, when work equals 0, when the force done on the object is perpendicular, like that. If I am here, standing here, having an object in my right hand, the weight is downward, and the force in my arm is upward, lifting force, and I am moving in this direction. Here is the displacement. So if you're gonna calculate the work for this process, work gonna be Fd cosine theta, and the angle is 90, theta equal 90. So the work gonna be Fd cosine 90, which is 0. There is no work done. Work is 0 when the direction of force is perpendicular to the direction of the displacement. The work is positive when theta is between 90, less than 90, and greater than 0. Work done is positive due to the angle of direction, the angle between the direction of the acting force on the body and the displacement is less than 90. So cosine is positive value. Remember the Aztec rule. Here all angles are all trig functions are positive. Here is in the second quarter the only sign cosine, and here is tan. All sine, tan, and cosine. So if you are in the first quarter, angle between less than 90 and greater than 0, the work done is positive. When the work done is negative, when the angle theta is greater than 0 and greater than 90 and less than 180. Here is the displacement, and here is the force. If you have an object here, car, and you pull this car in that direction, work Fd cosine theta, and theta in the second quarter is negative. Whereas work is negative, another position. If you have object here and it's moving in this direction and the force in this direction, so the angle between them is 180, and the cosine 180 is equal to -1. So the work is negative direction, like friction force. If you have a car here moving in this direction and you apply the brakes, the angle gonna be 180, and work is Fd cosine 180, which is gonna be -Fd. The last picture here, which is greater, work done on pushing an object forward or dragging it behind. If you have someone here pushing an object like that, or the person who dragging the object behind. We're gonna explain this. Here is the object. It has a weight here, and the acting force is in this direction, inclined by angle. And we have the object here, and here is the weight, and the person is lifting this or dragging this from behind. If you resolve this component, you have here theta, this is F cosine theta, and this is F sine theta. If we have here an angle theta, this gonna be F cosine theta, and this gonna be F sine theta. So the person who's pushing an object forward is doing much greater force, much greater work, as here these two components are in the same direction. Those two components are in opposite direction. So the fraction here is greater than the fraction. The fraction when pushing the object is greater than when dragging it behind. That's all for work, and see you in the next session. Thank you.